Okay, good morning once again. We are finishing up the topic of equilibria and we are going to look at ionic equilibria. Now, we were all along, those 5 videos that we did were trying to look at the chemical equilibria. Now, this is ionic equilibria. And ionic equilibria, we talk about acid and base. That's why sometimes we call it acid and base what? Equilibria. Okay. Now, we have some definitions that we are going to see that are even going to form part of this topic throughout until when we finish it. It's just a simple topic. We don't dwell much in it. It's just we want to see how equilibria is applied also to acids and bases. One, we will start with defining an acid. An acid is a proton donor. Now, acid, first of all, there are many definitions that you will find in different books, but they depend on different theories. Okay, yeah, we have Arrhenius theory, we have other theories also, but in this case, for our syllabus, we look at the Bronsted-Lowry theory. That's what we look at, and according to Bronsted-Lowry theory, he gave a general definition of an acid which qualifies for every part of species that will form to be an acid, and also for the base. So this is what we use throughout until when you finish your chemistry, maybe until when you grow gray hair. So we're gonna say an acid is a proton donor, and that's the definition that we're gonna take. A proton donor here, we're meaning a proton is a hydrogen ion or H plus. That means we will only look at how hydrogen is donated. Now, if you check this equation here, we have HCl, we have water, we have hydroxonium ions formed, we have Cl minus. It means HCl has donated H plus to water, giving us H3O plus. Remember, the plus is coming because now water is having more hydrogens than it's supposed to contain. So the H plus, the whole molecule gets the plus, and then it forms a coordinate bond. That's why we have hydroxonium ions in here. The HCl becomes Cl minus aqueous in there. Please, states are very important in here because we are dealing with aqueous solutions. So spot states are very important if you are doing this part of acid and base equilibrium. Now, a base is a proton acceptor. So it means in this case water is accepting a proton, so it is a base. It's accepting a proton from HCl. Still we are going to form the same thing. Now, number 3, we have an amphelite. You must have gone through this. I think maybe you must have seen it somewhere, maybe in your lower grades, whereby you discuss water as that it can act as an acid, at the same time it can act as a base. So a substance that can act in that form is what we call an amphelite in that case. So an example is this one. If we can be asked to write examples of how water can act as a base and at the same time as an acid. So we can check the first one here. Water in this case is what? Is a base because it's accepting what? A proton. Then in part B, if you check here, water is donating a proton to ammonia, giving us NH4 plus. Remember here I'll put something which is the double arrow in here because we'll see later that this one is known to be a weak base. In this case, it's an acceptor, it's a weak base, so that's why we put those double arrows. So water is an acid in this case, and that's why we say it is an amphelite. Number 4, we talk about conjugate acids and conjugate bases. Now, if I go back to your math, a conjugate means if I have -2, a conjugate of -2 is +2 in that case. So let us consider that and see. Consider an equation, this one here. We have here. Now, conjugate, please, I normally use it when we are considering either it could be a double arrow, it could be a single arrow, it doesn't matter. But we want to see. Now, if I have ammonia reacting with water to form NH4 plus OH minus, I will check. In this case, ammonia is a base. It's accepting a proton from water. Then water is an acid, is accepting a proton from, is donating a proton. So meaning, if I go this side of the equilibrium, I go on the right hand side of the equation, this equation is reversible, so it means I can go back to this equation. It means in this, if I go back, OH minus should accept a proton to go back to water. That means it is a base. Then NH4 plus should release that proton that they accepted before as ammonia to go back to ammonia. That means it is an acid. Now, we consider conjugated acids and bases when we are dealing with the equilibrium in here. So that is, we are now dealing with the ionic equilibrium now. So what's going to happen here? It means NH3 is a base, but this side it will act as an acid on the product side. Water is an acid, on the other side it will act as a base. Now this concept here is what we call the conjugate acid base concept, or we can call it acid 1 base 1 base 2 acid 2, or acid 2 base 2 concept. That's what we have in here. So in this case, what we see in here, water is a conjugate acid of OH minus, because we start from water. Water is a reactant, is an acid in here. So water is a conjugate acid of the base, because the conjugate, we say the conjugate of a minus is a positive in that side. So it means also here, conjugate of an acid is a base. So that's what we have in here. And NH3 is a conjugate base of an acid. And that's what we have in here. Please, you can be asked to write equations to show the conjugate pair, or they write for you an equation, you show the conjugate pair of either the acid or base, or they ask you to write acid 1, acid 2. Now the naming doesn't matter. I can take this one as acid 1, and then I take this one as base 1, or I take it as acid 2, and then this one will be base 2. But you must be consistent. If this is base acid 1, then this will be base 1. If this is acid 2, then this will be base 2, like that. And then the rest will now take the number depending on what you have chosen in the first one. Then number 5 is a strong acid. A strong acid is that acid that dissociates almost completely in the solution. And the examples of strong acids that we have sulfuric acid, HCl, hydrochloric acid, and then nitric acid. In this case, the position of equilibrium will be more to the right hand side. We don't need to put now a double arrow here, because almost completely the reactants will turn into products. Okay, in our next video we are going to see number 6, which is a weak acid.